Welcome, Hornets, and thank you all for joining me today. We're going to be talking about the alternating series remainder theorem and how we use that in order to find an answer within a specific range, as well as to find an error bound. So what we're going to do is we're going to start off by looking at the actual theorem for the alternating series remainder. And here it is. If a convergent alternating series satisfies the condition that a sub n plus 1 is less than or equal to a sub n, then the absolute value of the remainder r of n involved in approximating the sum s by using partial sums s sub n is always less than or equal to the first neglected or omitted term. That means that the difference between the actual sum and our partial sum will always be less than a sub n plus 1. So let's now just try to figure out what that means. We're going to do this graphically, okay? So I've already taken the opportunity to identify and find a series and get it set up. Now, you'll notice our first term is 1, and that is also my first partial sum. So if I were to graphing the partial sum, just like we did when we were doing our sequence mode, remember that? And we were working with the recursive formula to find partial sums. Well, this is what's happening. Notice the next partial sum, when I subtract 1/4 from the 1, will give me 3/4. Now, if I keep doing this, what I'm going to notice is that the actual sum, the infinite sum, is somewhere in between these two numbers. Now, I can't say it's exactly in between, but I know it is in between. So that means that here I have my first term, s sub 1, and that was made by a sub 1, going from 0 all the way up. The second term is s sub 2, and that is a sub 1 plus a sub 2. And if I move up, I get s sub 3, and that's made by a sub 1 plus a sub 2 plus a sub 3. If I then find s sub 4, it's going to jump back down again. And I now have s sub 4 is equal to a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. 5 jumps up again, and I have s sub 5. Once again, the sum of all of my terms. But what I want you to notice here, and this is important, is that if this is a sub 1, and I am trying to find the next partial sum, and I add at a sub 2, this piece right here, the green piece, is a sub 2. And that's what brings me down to s sub 2. Then, when I add a sub 3 from s sub 2, jumps up. And this is a sub 3. A sub 4 brings it down. That's a sub 4 right here. And then here's a sub 5 bringing it back up again. Do you notice anything special? How about the error between the partial sum and the actual amount? That error is right here. Do you see that error for a sub 1 is less than a sub 2? The error between s sub 2 and our total sum is less than a sub 3. The error between a sub 3 and s is less than a sub 4. The error between s sub 4 and the total sum s is less than a sub 5. So once again, what we're looking at is the difference between the sum and the partial sum, s sub n, is always less than the next term in the sequence. So the sequence is a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. So the sum S sub 4, which only uses the first 4 terms, has to have a sum. And that sum, when subtracted from the total, is going to be less than A sub 5. All right, let's just keep going. So that's what's happening. We're going to use that now. That idea that the next term is less than the error. Let's look at the problem that I have set up for us so far. We have approximate the series, and you'll notice it's the same series, within 1,000th of the actual sum S. Then state the error bounds. Now, first of all, please remember we're only looking at A sub n and A sub n plus 1. All right, we don't want the negative 1 to the n plus 1. We don't want that, so we're going to use the absolute value. And I'm going to take 1 over n plus 1, the quantity squared. That's the next term. And this next term has to be less than 0.001, the error that I'm looking for. Well, if that's the case, then I can flip them upside down. And n plus 1 squared is now larger than 1,000. If I take the square root, n plus 1 is larger than the square root of 1,000. And if I subtract 1, n is greater than the square root of 1,000 minus 1. But our n values are supposed to be discrete. That means they're natural numbers. They're exact values. 1, 2, 3, 4, 5, 6. And this is going to give me a decimal. In fact, when I take the square root of 1,000 and I subtract 1, I get n is greater than 30.6228. That means that n has to be the next largest value, 31. What this is telling me is that the actual sum minus S sub 31, the sum of the first 31 terms, is less than or equal to A sub 32. Now, I've already gone through the effort, and I've found what S sub 31 is. S sub 31 is approximately 2.1132, and A sub 32 is approximately 0.00097656. And you'll notice A sub 32 is less than 0.001. So I've now found how many terms I need to add together so that my answer is less than this error. So what's the error bound? Well, what we're going to do is we're going to take the sum that we found, S sub 31, and we are going to subtract A sub 32 from it. And then we're going to find S sub 31, and we're going to add A sub 32 to it. This is going to give me my boundary. What is too low, what is too high, and the actual answer is going to be in between the two. So if I take 2.1132 and I subtract 0.00097656, I'm going to get approximately 2.1034. If I then take 2.1132 and I add to it 0.00097656, I'm going to get 2.1229. I now know the actual sum is in between these two boundaries. These are my error boundaries, or my error bounds, and this is the number of terms that I need to add together so that my total sum, S sub n, is within 1,000th of the actual answer S. That's what we're trying to do, and that's what we have to practice. So as you are working in your work, you will notice that on page 695 of our textbook, they are going to ask you in numbers 31 through 36 to use this theorem in order to find the number of terms n that will give you a sum that is within an error less than 1/1000th. So I recommend you give a few of these a try and see how they go. We'll be talking about this and we'll be doing them more in class. Thank you very much. I hope this helps. Please be well and be safe and take care. The next video will be on absolute and conditional convergence. Thank you and have a good night. Bye-bye.